Okay, so we already used the Gauss's law. We derived Gauss's law, and then we used Gauss's law to calculate the electric field created by solid charged sphere, okay, at a point inside and outside the sphere. That's what we did last time. So now we're going to practice Gauss's law again, because Gauss's law is still a very abstract, okay. You don't find like everyday equivalent. It's not intuitive at all. So that's why we need to do a lot of practice on it. Now we're going to practice with this rod, okay. We actually did find the electric field created by a rod using superposition principle, right? And that's actually the first problem we did, using superposition principle to calculate the electric field from a continuous charge distribution, okay? So we did integrate that, and then wrote everything in terms of one variable, and then you look it up into a table, and then plug the upper and lower bounding, and at the end find the electric field. So that took us a lot of time to do that, right? Now we're gonna find the electric field from this rod using Gauss's law, okay? So in this case, we're gonna see that it's gonna be a little bit easier, okay? That's the whole point, right? So take a look at the rod on slide 20, okay? This is still the same rod. Now we're just gonna assume it's very long, and then it has a linear charge density. We already know the linear charge density, okay? It's a very long rod, okay? Okay, say it's positively charged. Now it's very, very long, okay? So it has a linear charge density lambda E. So we want to find the electric field at the distance d from the rod, right? Like here, at this point, at this distance d, okay? How do I do that? Okay, so first of all, I know how to find the direction of this electric field using the symmetry, right? You pick a charge at the top, okay? The electric field is going to be cancelled, y component cancelled by this guy. So for everything, every little piece, small element I pick at the top, I can always find another one on the other side to cancel the y components. So only x components left. So you add all these x components together. So I know that at this point, the electric field, it's always going to be in that direction. That electric field, right? Always. And because we assume this is a very, very long rod, right? So actually, even if you pick a point here, you can always find a pair from the top, from the bottom, pair them up. So the electric field is going to be y components cancel, x components add. So it's still going to be in that direction. Assuming this rod is very long, right? And you're only interested in this small region of this electric field, okay? So approximately, you can always cancel the y component. You can always find a small piece from this portion, and then another piece from this portion. You can cancel the y components. So okay, so that's the electric field. So it's always going to be away from the rod, right? If it's a positive charge rod, it's going to be in that direction. Now I want to find the magnitude. The direction is easy to figure out. We have done that many times, right? Use the symmetry. You can always find the direction of the electric field. Now what about the magnitude, right? So now I don't want to use superposition principle. I don't want to do this integral, right? I want to use Gauss's law. In order to use Gauss's law, you would have to find a Gaussian surface, right? This Gaussian surface doesn't have to be a real surface. I emphasize many times. So it's very hard for people to work with imaginary things. That's why we use math. We don't use our senses. We don't use our intuition. We use math to go way beyond our senses, okay? So I want to draw a Gaussian surface like what I did with this solid sphere, so that first of all, I would put this point on this Gaussian surface. Secondly, I want to make the electric field are constant, like the angle constant, so I can take them out, right? I don't really need to integrate anything. I only have the integral of this dA there, which is going to give me the area, okay? Now, so what is the Gaussian surface we want to draw, okay? So again, using the symmetry. If I pick a point here, that's going to be, the electric field is going to be in that direction, right? If I pick a point here, right, which has the same distance from the center, so the electric field is going to be outward, still outward, have the same direction, right? And if I pick a point here, the electric field is definitely going to be outward in that direction. And I pick a point on the other side, okay, even inside the board, right? The electric field is going to be in that direction. So if I put all these points together, what do I get? I actually get a cylinder, right? So if you draw a cylinder with this rod through the center, then on this curved side of this cylinder, every point, the electric field is going to be outward, 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 outward. And the magnitude must be the same because every point is going to be equivalent, right? So take a look at the image on slide 21. So that's going to be the Gaussian surface I draw. I draw a cylinder, okay, with this rod crossing the center of the cylinder, okay? So it's pretty much like this. I have a rod, has a long rod, longer than this, okay? I'm going to draw, this is my Gaussian surface, totally imaginary, it doesn't exist, right? I draw a Gaussian surface with this rod, okay, totally through the center. So that's going to be my Gaussian surface, right? So for every point on this Gaussian surface, right, if this rod is through the center, for every point on this Gaussian surface, you're going to see the electric field this way, this way, this way, this way, outward. And the magnitude should be all the same, right? Because they are totally equivalent, okay? So that's the Gaussian surface I draw. But I need to make sure the Gaussian surface is closed so that I can apply this law, right? So you always draw closer. Well, I'm just going to include the top and the bottom, right? So it's a whole cylinder, not just this curved side, okay? So that's the Gaussian surface I draw. Totally imaginary, doesn't exist. Okay, fine, that's a mathematical concept, right? Okay, it's going to take you some time to get used to these invisible things, imaginary things, okay? But that's totally math. So that's going to be the Gaussian surface I draw. Okay, now every point on this curved side, you see that they will have the same magnitude of electric field. Now, then I can go ahead and then apply this law, right? So the left-hand side, okay, don't be scared by the left-hand side. The left-hand side actually is always easier than the right-hand side. Remember what we did the solid sphere. The right-hand side is, can be tricky if the charge inside the Gaussian surface is not given by the problem, okay? You have to find that, okay? The left-hand side, it's always gonna be one of the special cases, okay? So in this case, you will still get E dA cosine theta, right? So in principle, you should calculate the electric flux on the left-hand side through this whole cylinder. So you're going to do 3 surfaces, right? Don't forget the top and bottom and the curved side, right? So you need to do 3, you need to integrate the electric field on 3 surfaces, top, bottom, curved side, okay? But at the end, okay, you're going to do the top, you're going to do the bottom, okay, and then you're going to do the side, the same integral. Okay, so that's the complete electric flux through this imaginary Gaussian surface I drew. But the top and the bottom, you see that it's a special case, right? The electric field is totally outward, right? So what is the flux through this surface, the top and the bottom? The electric field is this way. That's parallel. If the electric field is parallel to the surface everywhere, you don't need to calculate that. 0. Always 0, right? There's no single line passing through the top or the bottom, right? So these two guys, you get 0 and 0. Okay, nice. So the only thing you need to calculate, it's going to be the curved side. So you're going to still do E, dA, cosine theta, okay? But again, you don't need to do that, right? Take a look at the relation between the electric field and curved side. Perpendicular again, right? So the electric field is going outward. This is the curved side, perpendicular again. If it's perpendicular everywhere, what is the flux? E times A, always, right? Or you can do that, right? E is a constant, right? Take it out, you get dA sine theta, right? You can do that. Now, what is cosine theta? This is E. What is the direction of the dA at this point if you pick this small piece? dA is in this direction, outward, perpendicular. What is the dA at this point? Outward, perpendicular, outward, perpendicular. Again, they make 0 degree angle, right? No, not cosine, by the way. Cosine. Okay? So because the electric field is perpendicular to the surface everywhere, it's going to make the angle theta 0, right? Because the angle theta is the angle between E and dA, okay? So don't get confused. This can sound confusing, okay? The electric field is perpendicular to the surface, true. But the angle in this equation is 0. It's not 90 because we are looking for the angle between E and dA. dA is defined as perpendicular to that. But all I need to do, this is a shortcut, right? I said we can remember. If the electric field perpendicular to the surface everywhere, okay, E times A at the end, right? Because you're always going to get this. You take out E cosine 0, you get dA, right, inside, only dA inside the integral. So you will always get E times A. Now in this case, you only need the area of the curved side. You don't need the top and bottom because their contributions are 0. Okay, so now you just divide both sides by this curved side, the area of the curved side. That's going to be your answer. But again, you should make sure all these symbols, you're going to use all the symbols from the problem, right? You can't use like Q in and curved side because you don't have that in the problem. The problem doesn't say what is the area of the curved side, what is the charge of this Q in. So let's take a look at the area of this curved side. The curved side, if you remember, how do you calculate the area of a curved side? Well, if you open up this curved side, what do you get? You actually get a rectangle, right? This is going to be the curved side of a cylinder, right? If you wrap it up, you open it up, becomes a rectangle. So the curved side of a cylinder is just going to be length times width. So the length is just going to be the circumference of this bottom or top, right? And the width is just going to be the height, okay? So in this case, the area of the curved side is going to be 2 pi r. What is r? Well, it's going to be this radius, right? Because I want to put this point on this curved side. So apparently, this is going to be the radius of the cylinder. And then this is the length times the width, which is the height of this guy. So the height of this guy, let's call it h. Okay, so I introduced the arbitrary variable h, which is not given the problem, right? So it looks like I'm introducing a new variable which makes the question more complicated. But at the end, this h is gonna cancel, okay? So let's see, this is gonna be the curved side. So Q in over epsilon naught 2 pi d times h. So that's the area of the curved side. You still have Q in here. You haven't found a Q in, right? So now let's see. How do I find Q in? What's the definition of Q in? Everything has definition, okay? Use the definition, okay? Go ahead and find it, okay? That's why I like physics. I don't need to define anything, okay? I don't need to interpret these names, okay, based on my own understanding. You don't, because everyone's going to have a different understanding, right? There's a definition. Just use the definition. Everyone gets the same answer. This is a Gaussian surface. So I want the charge inside the Gaussian surface. What is the charge inside the Gaussian surface? Only this portion of the rod is inside the Gaussian surface, right? This portion outside. This portion outside. So it's not a single charge inside the Gaussian surface, but by the definition, any charge inside the Gaussian surface is going to be this Q in I need in that equation. So all I need to do, just calculate the charge on this piece, on this segment, right? How do you find the charge on this segment, okay? Well, again, that's when we use this lambda E, right? How do you already know the linear charge density of the rod is lambda E. You don't need to even need to divide Q by L because the problem already tells you it has a linear charge density lambda E. Go ahead and use that. If you have lambda E of this whole rod, linear charge density, I want you to find the charge on this segment which has a length H. How do you find that, right? You already know that. We have done that many times, right? Once you find that, that's the expression of Q in. You plug in, and then you're going to divide them. You're going to cancel out this H. That's going to be the final expression, okay? So that's the question I want you to answer on slide 22, all right? Now, as I said, how do I find this charge? This charge is the Q in, right? If I already know the linear charge density, multiplied by the length of the segment you want me to find, right? That's going to be the charge on this guy, right? Imagine, as I said, if the linear charge density, say, is, I give you some numbers if it's hard for you to understand. This is 5 coulombs per meter, and the H is 2 meters. Okay, this whole rod has a linear charge density. For every meter, it has 5 coulombs. What is the charge on 2 meter segment? Of course, that's going to be 5 times 2. 10 coulombs, that's the total charge on this 2 meter segment, right? So all you need to do is just multiply the linear charge density by the length of the segment you picked, right? So that's going to be what I plug in here. So the electric field at the end, okay? I'm going to continue here. Lambda E H epsilon naught 2 pi d H. Cancel the H. It shouldn't be there in the final answer because this H totally depends on how large you draw this cylinder, which is totally arbitrary, right? The final answer shouldn't depend on that, and it's totally imaginary cylinder. So this is the final answer, right? This is the final answer. All right, so that's our conclusion. For a very long rod, very long, the electric field created by this rod at a point which has a distance d, perpendicular distance d from the rod, is going to have this magnitude and the direction outward. Right. Now, if you compare this with the conclusion we drew using superposition principle, which is on PowerPoint 3. PowerPoint 3 slide 5, right? So we calculated the electric field, okay, from a rod, and then we took the limit. If the rod is very long, what do you get? You get 2 times Ke and then lambda E. So that's what we derived using superposition principle, right? If you look at the slide 5, PowerPoint 3, when the rod is very long, you get 2 Ke lambda E over d. And they're equivalent because Ke and epsilon naught, they connected, right? Ke equals 1 over 4 pi epsilon naught. You can show that they are exactly the same. Okay? So which agrees with the result we got using superposition principle. But this, it's much simpler, right? We actually didn't do any integral. Okay, we just used the conclusions for these 3 special cases, and then so actually the tricky part is always the charge inside the Gaussian surface. That's always the tricky part. Okay, so that's a rod. Now let's see. We're going to take a look at another example, and again we're going to compare the conclusion to the conclusion we drew using superposition principle. Okay, now that's a very large plane, okay, so that's slide 24. A very large plane, how do you find the electric field created by this plane? Now I'm going to erase this. So a very large plane has been charged uniformly, say positive. So I want to find the electric field at a point, again, which has a distance d from the plane, okay, from the plane. Now, direction, easy, right? I know that you can even guess that because we have done so many problems. You can pick this guy and this guy. They're going to have electric field going this way and this way. Y components cancel, only X components left. And this is we assume this is a very big plane. So that means for any point you pick here, you can always find one at the top, another one at the bottom, cancel out these Y components, only X components left. So at the end, the electric field at this point, always in that direction. Okay, so if this is a very big plane, I'm only interested in the region, in this small region, the electric field at any point, if it has it's always going to be outward, right? So the electric field at this point, on this side, it's going to be outward, okay? So away from this positive plane. Now, that's the direction. Direction is always easy. Now I want to find so this is still d, this distance, okay? Now I want to find the magnitude. So again, I want to use Gauss's law. I don't want to use a superposition principle. Actually, we already did superposition principle. So I would want to draw an imaginary Gaussian surface. And then I want to, first of all, I want to put this point on this imaginary Gaussian surface. Secondly, I want to make sure that I can have all these points on this Gaussian surface have the same magnitude of electric field. So I can still do this, right? Take out this E, and then make sure the cosine theta is a constant, take it out, right? So again, I would just have only dA inside the integral. That's going to give me area. So we have done so many problems, so that's going to be our strategy. So as I said, okay, this point, if it has the same distance from this, that's going to be, they will have the same magnitude, right? So, and this point and this point, what's the difference between them? There's no difference between them, right? So if I do that, so I can draw a circle, right? It doesn't have to be a circle. Like a rectangle is going to do that, right? So if I draw a circle, right, parallel to this plane, any point on this surface, right, which is parallel to this plane, it's going to have the same magnitude of direction and also direction, right? Electric field is going to be in that direction, and then the magnitude is going to be always the same because every point is going to be equivalent to each other, right? But this is not enough. If I want to use this Gauss's law, I have to make sure that I pick a closed surface, right? This is an open surface. So how do I draw a closed surface? Again, let's make a cylinder, right? I'm going to pick all these points on the other side. Also has a distance d from the disk, and also draw a circle here, and then make a cylinder, right, out of these two circles, right? So now this is the cylinder, right? The cylinder is sitting this way, so cylinder crosses this, passes through this plane, okay? That's my Gaussian, so that's a closed surface. That's a closed surface, okay? So now I'm going to use Gauss's law to find the electric field. So at any point on this circle, or this circle, right, because they are equivalent, they will have the same magnitude of electric field. set it up the same way, nothing changes, and then because it's a cylinder, so I would still have to evaluate this flux on the top, bottom, and curved side, right? So this step doesn't change, right? Nothing has changed so far. Now this step is going to change because I'm not going to have 0 and 0 at the top and bottom, right? Because now you see that top and bottom, well, it doesn't matter which one you call top, which one you call bottom. They have the electric field perpendicular to them. So that's not going to be 0, right? But the curved side is going to have the electric field perpendicular to them, right? Because the electric field is going to be all radially outward. So the curved side doesn't have any flux. It's parallel to every single line. Every single line, no single line is going to pass through the curved side, right? So actually, I would get a 0 here, right? But the bottom and top, what do I get? We have done that so many times. I don't even need to repeat this. I will get E times A for the top, E times A for the bottom, right? Because the electric field perpendicular to the surface everywhere, it's always going to be E times A. This is 0. Curved side is 0 in this case. Right? Okay, so this is what I get if I evaluate this integral on this cylinder, but still I didn't evaluate integral anything, right? Integrate anything. I still use the conclusion for one of the special cases we see. Now, okay, but the bottom, the curves, the top, they have the same, it's a cylinder, right? They have the same area. So I'm just going to use 1A. So I have 2 E times A on the left-hand side, right? Now the right-hand side, Q in over epsilon naught. Okay, how do I find E? Don't forget what we're doing. We are using Gauss's law to find the electric field. I'm just going to do this, divided by epsilon naught times A. Okay, how do I find the A and curves the Q in? Okay, so the problem, let's see what the problem gives us. The problem gives us the plane has a positive surface charge density sigma E. So this guy has a surface charge density, right? So I would use that. And the distance D is this distance, okay? So first of all, how do I calculate the area? The area is going to be the circle, right? So, okay, so I should know, I need to know this radius of this circle. But this is totally arbitrary. This is a circle I drew, right? So the radius should be, you know, totally arbitrary. It's not going to be a number from the problem, but that's fine. Let's just call it R, okay? So the A is going to be pi R squared for sure, okay? So that's what I'm going to plug in. So from the experience, okay, we gained in the previous one. So I guess I'm confident this R is going to be cancelled at the end because this is the totally arbitrary. The final answer shouldn't depend on the arbitrary variable I introduced when I solved this problem, okay? So that means this Q in should have this R, right? So how do I find Q in? Where is Q in? This is the Gaussian surface. It passes through this plane. So there is some charge inside this cylinder, right? So only in this portion, it passes through this disk. So only in this portion of the plane is inside this cylinder. It's inside the Gaussian surface. So I only include this charge in Gauss's law on the right hand side, right? How do you find this Q in? You already have surface charge density, right? We just did linear charge density. If I have linear charge density on a big rod, long rod, I want to find the charge on a very small segment. I just multiply the linear charge density with the length of the segment. Now I have a big plane. I know the surface charge density, but I only want to find the charge on this very, very small area, very small surface. How do you find the charge? of course, you're going to do sigma E times the area. And this area is the same as the top or the bottom, right? It's obvious, okay? So that's going to be sigma E also pi r squared. And this r is going to be the same as this r. Now you see that they should cancel at the end, right? Now you put all the symbols in, you should find the answer, okay? So that's a question I want you to finish on slide 25, but this is very obvious. I already pretty much did all the work. All right, so you put everything in, you should get pi r squared, and then, oh, there's a 2, sorry. How did I miss that? 2 epsilon naught pi r squared. Now you see that this cancels this. What do you get? Sigma E over 2 epsilon naught. So that's the electric field created by a very, very big plane, right? So it's going to be outward, the magnitude is going to be the same, right? So actually it doesn't depend on the distance. You see that? It doesn't have the d. So even if I pick a point here, that's going to be also sigma E over 2 epsilon naught. Again, by assuming the plane is very, very large, and I'm only interested in a very small region close to this plane. And again, if you compare it to the conclusion we drew using superposition principle, which is still PowerPoint 3, but now that's going to be slide 10, okay? So we didn't really derive that, right? I just presented the conclusion. So for a uniform charged disk, the expression is that it's a long expression, but if you take the limit when the disk is very, very large, which is what we have here, right? So the plane is very large. When it's very large, so it doesn't matter what shape it is, right? You will get sigma E over 2 epsilon naught, right? And that's actually how we derived the equation for parallel plate capacitors, right? If you have 2 of them charged with the same amount of charge and opposite signs, you actually have this from one plate and the same value from another plate. They are in the same direction, they add together. That's why for parallel plate capacitor, you have sigma E over epsilon naught, right? But for one plane, you only have sigma E over 2 epsilon naught, right? So we didn't really derive that, the electric field from a uniform charged disk, using superposition principle, but I told you you can do that. The idea is that you think of as made of a lot of rings with different radii, right? You use the conclusion of the ring, and then you make this radius of each ring as a variable. So at the end, you will have a function of r and times dr. You're going to integrate that over dr. So it's very complicated. That's why we didn't do that. Okay, but anyway, you can derive that using superposition principle. It's very complicated. But if you use Gauss's law, you don't have to do that, right? So you just pick a very nice Gaussian surface. The left-hand side, even though it's an integral, it's always going to be one of these special cases we have seen in this class. Okay, you never need to evaluate an integral. It's always going to be e times a or 0, e times a or 0, okay? And then the right-hand side actually is tricky. Okay, you have to find a way to evaluate this Q in if the problem doesn't give you the Q in directly. Okay, so actually when you apply Gauss's law to find the electric field, the right-hand side is harder than the left-hand side. Okay, left-hand side is always going to be one of the special cases we have seen. All right, so that's this. Okay, so we have finished Gauss's law. Now we're going to move on to the next topic. Okay, so we're going to move on to PowerPoint 5, electric potential and electric potential energy. Okay, why are we interested in electric potential and electric potential energy? Okay, first of all, there's a fundamental theory in physics. For any conservative force, okay, you can always define a potential energy and a potential, okay, associated with this conservative force. That's a fundamental theory. Okay, so what is conservative force? Okay, if the work done by a force between any 2 points is independent by the path taken, and the work done by this force through any closed path is 0. That's a conservative force. Okay, so we don't need to know how to determine if a force is conservative in this class. Okay, so but there are some conservative forces we discussed in physics 1. Gravity is a conservative force. That's why we defined gravitational potential energy. Okay, so spring force, the force in a spring, okay, it's the restoring force in a spring. It's also a conservative force. So that's why we define elastic potential energy, right? And then electric force is also a conservative force. So that's why we can define electric potential energy and also electric potential we're going to define, okay? So there are also other forces that are not conservative force, like friction, normal force, right? We never define like frictional gravitational potential energy, right? We never did, okay? Or normal potential energy, okay? We never did that. So how to define potential energy and the force, okay? There's a relation between them, okay? So that's totally mathematical, okay? So you can take a look at these 2 equations on the first slide, okay? If you have the expression of the force, you can use this theory to find expression for the potential energy. Or if you have you just integrate the force, okay, along this dr. If you have the expression for the potential energy, you can take a derivative, okay, of this potential energy, okay, in every direction, x, y, and z, okay, 3-dimensional, and then you will get the force, okay, in every direction. It's going to be vector, okay. So that's a complete theory in physics, okay. We're not going into details about this theory, okay, but that's the reason we can define electric potential energy, okay, in this part, okay. So then that's going to be the definition of potential energy. So we're going to first define that using the definition, okay, using the fundamental theory, and then we're going to see why we are interested in potential energy, okay, and electric field. So if you apply the fundamental theory in the first slide, okay, in electric field, so all you need to do is this, right? So the potential energy, because potential energy is relative, okay, the actual value of a potential energy at any point depends on the reference point you pick. So when we define potential energy, we always define the difference between any 2 points, because that's absolute, okay? That value is always unique. You don't get any different values if you pick a different reference point. So if you have a point A and B, the difference in the potential energy, okay, between these 2 points, if you move a charge Q0, okay, from point A to point B, okay, the potential energy difference is always defined as this. So you just integrate the electric force on this charge, okay, along a path from A to B, and because the work done by this electric force doesn't depend on the path taken, right? That's the definition. That's the definition of conservative force, remember? So you can pick any path, okay? So it's totally arbitrary, okay? So there wouldn't be any ambiguity, okay? Even if you take a path, I take a different path, we evaluate this integral, we will get the same answer, okay? So it's a consistent theory. Everything is consistent in physics, everything, okay? So once you have done that, so this is going to be a scalar, okay? This is going to be a scalar because you do Fe dot dr, right? This is going to be a scalar product, right? This is a dot product. You're going to get a scalar, pretty much like the flux. It's a scalar. So this guy is going to have a unit which is going to be joules, right? Because this is still energy. So this guy is still going to be in joules. Okay? Now, as I said, only the difference in electric potential energy or any potential energy is meaningful. The actual value of a potential energy at any point, at a specific point, depends on zero reference, right? So think about the gravitational potential energy we defined. That's how we define it, right? mgh in physics 1. So, okay, the mass, okay, it's like 5 kilograms or something. G, if you're on the Earth, that's going to be 9.8. What about this height? Okay, so how do you define height? Well, you would say, well, if I'm in this room, I'm going to define height from the floor, right? So say I have something here, I want to calculate the gravitational potential energy. I would just say, okay, it has 1 meter from the floor. So that's going to be the height I plug in. There's nothing wrong if I use this table as the zero reference, right? So I would say the height of this guy relative to the table is going to be 10 centimeters. That's going to be the number I plug in. Or think about this. If you are on the 10th floor and I want you to calculate the gravitational potential energy of something, you can still do that. You can still pick the floor as the reference point. So something has a height like 1 meter. It's pretty much like here, right? Have 1 meter from the floor. You would say, okay, mass times 9.8 times 1 meter. But if I'm on the first floor, okay, I'm watching you doing this experiment, and then I would say, wait a minute, right? The height of the object you're measuring, the height is not 1 meter, right? Because you see that this is first floor. You should count from the first floor, right? So it's going to be, you know, hundreds, more than 100 meters, maybe, okay? So we're both right. We're both right, okay? No one is wrong because the actual value of the potential energy totally depends on the zero reference point, right? If I ask you, I have an object here. What is the position of this guy? Is it 5 meters, 10 meters, or 2 meters? You would say, where is your origin, right? You can draw origin here, you can draw origin here. You can say like the other room, that room is my origin. My origin is there, right? So the x-coordinate, the position of this guy is totally relative, right? You have to define a zero reference point. So the potential energy, gravitational potential energy, the actual value, even though we say, okay, the height, but what is the height, right? It's totally relative. You need to tell me where the zero reference is, right? So this height is relative. So this value you calculate is going to be relative. So different people can get different values. But if I calculate the potential difference between 2 points, right? I have an object here, and then I move it down here. I want to calculate change in the potential energy. That's going to be a unique number. Doesn't matter which reference points you pick, right? Doesn't matter who is doing this calculation. The change in the height, okay, is totally absolute, right? It's totally unique. Everyone is going to get the same number. So that's the point, okay? So for electric potential energy, it's the same idea, the same deal. So when we talk about the actual value of a potential energy, it's all about the zero reference point, right? So different people can get a different number. But if we calculate the potential energy difference between 2 points, everyone is going to get the same number, okay? So that means when you calculate electric potential energy, you can get a positive or a negative number. So don't freak out if you get a negative number, right? A lot of people, because they are familiar with energy, okay, they say, I don't know what negative energy is in my life, okay? Potential energy can be negative because it's a defined quantity in physics. You can define anything in physics, right? Temperature can be negative. It's totally because you define the zero as the freezing point of water, right? Anything lower than the freezing point of water, you can call it negative in Celsius, okay? So there's nothing wrong with that, okay? So that's the potential energy. So another thing we define is called electric potential, okay? Why do I define that? Because, so first of all, let's write down the definition. Because the force depends on the task charge, right? If you want to calculate the potential energy or the potential energy difference between any 2 points, you need a force. So in order to calculate the force, you're going to do task charge times the electric field. right? So if you have 2 points in an electric field, you want to calculate the potential energy difference between these 2 points, even the potential energy difference, you still need to bring a test charge in there, right? And if you bring a different test charge, the value is going to be totally different, okay? So in order to, we want to remove that information about this test charge. We want to have a quantity which is totally determined by the field, okay? So it's totally unique if the field is already set up, okay? We want to remove this Q naught, right? So we just divide this by Q naught. If you divide this by Q naught, what do you get? You will get the potential difference between 2 points. It's just going to be this over Q naught, right? And Fe divided by Q naught, that's just going to give you the electric field, right? So the potential defined this way is just going to be the potential, again, only the difference is meaningful. It's going to be integral of the electric field along a path between A and B. So that if I define this thing and I have some electric field here, I don't need to bring any test charge to calculate energy. I can just calculate the potential difference between these 2 points, A and B. If I know the electric field in this region, I just integrate that along a path between A and B. And the path actually can be any path, right? Because this is a conservative force. Okay? So the relation between this potential and potential energy is the same as the relation between the force and electric field, right? You see that field is defined as electric force over the test charge, so that the field is totally determined by the source. Once the source is given, electric field is given, right? You bring different charges at this point, it's going to feel a different force, right? And then the potential is pretty much like the electric field. The potential at this point is totally determined by the source charge. Has nothing to do with the test charge you're bringing, okay? So that's the difference between electric potential and electric potential energy. So when we talk about electric field, we're just going to talk about electric potential, right? Because that's a property of this electric field. It's totally determined by the field and the source itself. And if I want to use energy, okay, and then to do calculations, I can multiply that by test charge. So I'm going to bring a test charge in this electric field and then multiply the potential to get the potential energy. Okay, so that's what we're going to do. So we're going to focus on potential, because potential is going to be the hard part, right? Once you find the potential energy is easy. You just multiply potential by Q naught, okay? So the potential we define has a unit, which is going to be joules over coulomb, right? And we do have a new name for it. We call it volt. And the symbol for volt is also V. Okay, so I think that's the only case we use the same symbol for the variable and the unit. So sometimes you can see a potential at some point is like 5 volts. That doesn't mean V equals 5 times V. Otherwise, the solution is V equals 0, right? This means this is the potential equals 5 volts. That's the unit. Okay, all right. So I'm gonna stop here for this video.